Today, inshallah, we are going to study chapter 21, further aspects of equilibria. Okay. First of all, we are going to talk about something called the ionic product of water, which is Kw. What is the ionic product of water? Now, water by itself, when two molecules of water are present beside each other, one of the water molecules donates a proton to the other water molecule, and so it forms a hydronium ion plus the OH ion. It means that water is very, very slightly acidic. Of course, the acidity is so little in amount, but a proton can be removed from one of the water molecules and donated to the other water molecule. And in that case, it will form what we call a hydronium ion, which is the H3O positive, which is acidic, plus OH minus, which is basic. And so we can put this equation in a more simpler form, that the water ionizes into hydrogen ions plus OH ions. And as you see, there is equilibrium here because the ionization is so small in amount. Now, before we took, now we should have taken before. No, this is the chapter. Okay. Whenever we have equilibrium, we have something called equilibrium constant, Kc. What is the equilibrium constant? The equilibrium constant equals the concentration of the products times each other, raised, if there's any power here, if there is any coefficient here, it will be raised to the power of the coefficients. But here, in case of water, we don't have coefficients, so the equilibrium constant Kc equal the concentration of the hydrogen ion times the concentration of the OH ion divided by the concentration of water. When we write brackets in this way, this means concentration. Okay, so the Kc equal the hydrogen ion concentration times the OH ion concentration divided by the concentration of water. But from a moment we said that water dissociates so slightly to give the hydrogen ions and OH ions, so we are going to consider as if the concentration of water is constant. We are going to consider it to be constant. It means that as if no part of it dissociated. So the concentration of water is a constant. So if we multiply the concentration of water, which is constant, by the Kc, which is the equilibrium constant, which means that it is another constant, then Kc constant times H2O constant, there will be a new constant that we are going to call it Kw. Understand? When we take this water and let it go to the other side, then the concentration of water times Kc equal H positive times OH minus concentrations. But since Kc is a constant and the concentration of the water is considered to be constant, so constant times constant will give us a new constant that we are going to call it Kw, or the ionic product of water, which is equal to the hydrogen ion concentration times the OH ion concentration. Understand? Yes. You understood? Okay. Yeah. Now, Kw was found to be 1 times 10 to the power minus 14 moles squared, decimeter minus 6, at a temperature of 25 degrees Celsius, which is 298 Kelvin. So this is the value of the Kw. Now, if we look here at the hydrogen ion concentration and the OH ions concentrations, they are equal. When water dissociated, it gave 1 mole of hydrogen ions and 1 mole of OH ions, and this means that both moles are equal. So we say that Kw equal H positive times OH minus, or else we can put H positive square since both are equal. Since the hydrogen ion concentration is equal to the OH ion concentration from this equation, so we can remove the concentration of OH minus and put hydrogen ion instead. And so hydrogen ion times hydrogen ion will give us hydrogen ion squared. And this means that 1 times 10 to the power minus 14 equal the concentration of hydrogen ion squared. And this means that the hydrogen ion squared equal the square root of this value, which is equal to 1 times 10 to the power minus 7. So this is the concentration of the hydrogen ion, and also it is the concentration of the OH ions. And so we are going to introduce a value. Since this is a very small value, then we are going to take minus log of this hydrogen ion concentration, which we call it pH. We will find that minus log 10 to the power minus 7 equal 7. That's why when we say the pH of water equals 7, that's because these calculations. Okay, so the pH of water is equal to 7 because when we take here Kw equal the concentration of H positive times OH minus, and we exchange the concentration of the OH minus by H positive as both are equal, then we get Kw equal H positive squared. And since Kw at room temperature is 1 times 10 to the power minus 14, which is equal to H positive squared. So if I want to find the concentration of hydrogen ion alone, it's going to be the square root of 1 times 10 to the power minus 14, which is 1 times 10 to the power minus 7. And since the concentrations are very, very small, as you see here, 10 to the power minus 7, so we take the pH, which is minus log the hydrogen ion concentration, it will give us 7, and that's why the pH of water is equal to 7. Okay, understand, or shall I repeat it?
No, understood.
Okay. So here, the pH values means the minus log hydrogen ion concentration. Of course, every system has a different pH than the other. So if we, for example, take hydrochloric acid, 1 mole per decimeter cube, we will find that its pH is equal to 0. The stomach juice, pH between 1 and 2, lemon juice 2.3, vinegar 3, and so on. We have, as we said, water, it's 7. This is pure water. The saliva is 6.3 to 6.8. If we take soapy water, the soap is 11. Magnesia, milk of magnesia, which we take it whenever we have high acidity in our stomachs, it's 10. The pH of sodium hydroxide, 1 mole per decimeter cube, is 14. We will see that strong acids like hydrochloric acid or sulfuric acid or nitric acid, when we prepare them in 1 mole per decimeter cube, their pH ranges between 0 and 1. And sodium hydroxide, which is the strongest base, its pH is 14. That's why when we were studying in O level, we said that whenever we have a pH which is equal to 7, this means that we have neutral solution. From 0 to 7, we have acidic solutions. And from 7 to 14 pH, we have basic solutions. Of course, as we go away from the 7 value, whether towards the more basic solutions or towards the concentrated or the strong acidic solutions, whenever we go away from the 7, this means we are reaching a stronger value, a stronger acid or a stronger base. Okay. Now, how are we going to calculate pH? For example, when it says calculate the pH of a solution whose hydrogen ion concentration is 5.32 times 10 to the power minus 4 mole per decimeter cube. So at once we say he wants us to calculate the pH, and he gives us the hydrogen ion concentration of this solution to be this value. So the only thing that we are going to do is to write pH equal minus log hydrogen ion concentration. The P means, the P letter means minus log. And this is, of course, an arithmetic function. So we say that the pH equal minus log, and we write, we put on our calculators minus log and put this value between brackets and get out the value that is written in the calculator. It is 3.27, which means that this solution is acidic because it is less than 7.
Miss,
Yes.
I have a question up. Why is there a 10 next to the log? What is this 10?
We have mathematical functions. We have either len or we have something called log to the base 10. It means e to the power minus 10. These are mathematical functions. Yani they here minus log to the base 10 because we have two different mathematical functions. One of them is called len and the other is called log, and there is a relation between them that the len equals 2.303 the log. So these are mathematical functions. We don't have to mind them. The log is present in our calculator, so we use it as it is. Okay, these are mathematical functions.
But if I write it with the 10 ID, I'm still gonna get the same answer.
Yes, of course, but you are not going to find the 10, I think, in your calculator.
Oh, okay.
Your calculator is written log only. I don't mean it means 10 to the power something. Log to the base 10 means 10 to the power something.
Okay.
You understand? You will see the button in the calculator log. Beside it there is len. The log above it is written 10 to the power, and the len is e to the power. Okay.
Okay, thank you.
So just put them in. Just put the numbers in the calculator, and you will get the answer.
Okay.
Now, what if he gives us the pH and he wants the hydrogen ion concentration? Sometimes they give us the pH. It says calculate the hydrogen ion concentration of a solution whose pH is 3.27. So also in the calculator, you will find that there is a button that is called shift. Okay, so either you write shift log. You see there is a button at the upper part of the calculator is written shift. So you press the shift and then log, and then you put shift log and you put the number that he gave us in negative value, 3.27. Shift log, and then between bracket minus 3.27, you will get the hydrogen ion concentration. If you have a calculator in front of you, you can try it, either to write shift log, or else in other calculators, there is 10 to the power at once. Here, you are going to write 10 to the power minus 10.5. You have a button that is called 10 to the power. So you will press the 10 and you write the 10 to the power. You are going to press it and write minus 10.5. That's why the log is to the base 10, because it is 10 to the power minus the pH. Okay?
Yeah.
I don't know. You took it in school. Okay. So either you press the button at once, 10 to the power, and you write minus the value that he gave it to you. He said calculate the hydrogen ion concentration of a solution whose pH is 10.5. So either you press the button 10 to the power minus, and you write 10 to the power, and you write minus the value here, or else you press shift log and then between brackets write this value but in a negative one, minus 10.5. Okay, so you can try it in your calculator to get the hydrogen ion concentration. So either they give us the hydrogen ion concentration and wants the pH, or else they give you the pH and wants you to calculate the hydrogen ion concentration. Okay. Now, in order to calculate the pH of strong acids, because as you know, we have strong acids and we have weak acids. Strong acids like hydrochloric acid, like nitric, like sulfuric acid, phosphoric acid, these are strong acids. And we know from our previous studies that strong acids completely ionizes in water. Strong acids completely ionizes in water. It means if they are placed in water, they completely dissociate into their ions. For example, if I have hydrochloric acid, then it completely ionizes to H positive plus chloride negative. So it completely ionizes in water. It means that we put this arrow in going on one direction, because all of the acid, we can say all of the acid can be dissociated into hydrogen ion and chloride ion. Okay, so if we have a strong acid and we want to calculate its pH, of course, we use a device that is called pH meter. The pH meter is connected to an electrode that we just put the electrode in the solution that we want to measure its pH and read on our device the value. Of course, this is not a pH meter, but we have a device that is called a pH meter, and it has an electrode that whenever we place it in our solution, we can calculate the pH at once. But what if we want to calculate it by calculations? So just we take the minus log the hydrogen ion concentration. For strong acids only, we say that the hydrogen ion concentration is equal to minus log the hydrogen ion concentration. Okay, now, as we said here, if he wants us to calculate the pH of 0.1 mole per decimeter cube HCl, since HCl is a strong acid, so at once to calculate its pH, we say pH equal minus log the hydrogen ion concentration. So it's 0.1 mole per decimeter cube. This is the concentration of hydrogen ions, because as we said that HCl completely ionizes to give hydrogen ion and chloride ion. And this means that the concentration of HCl is exactly similar to the concentration of the hydrogen ions and the chloride ions. But we are calculating for the hydrogen ions, not the chloride. So we say that the pH equal minus log hydrogen ion concentration, which is equal to the concentration of the hydrochloric acid 0.1. And so we get a pH equal to 1. If we want to calculate the pH of a 0.01 mole per decimeter cube hydrochloric acid, it's the same. Hydrochloric acid completely ionizes to hydrogen ions and chloride ions. So if the concentration of the acid is 0.01, then the concentration of hydrogen ion is also 0.01. And this means that the pH equal minus log 0.01, which is equal to 2. For 0.001, the pH is 3. It's calculated in the same value. Now, what if we want to calculate the pH of strong bases? If I have a strong base, how would I know how to calculate the pH of this strong base? Because he's going to give us, since we have a strong base, for example, like sodium hydroxide, since it is strong, also it will completely ionize into sodium ion and OH ions. And so if he gives us the concentration of sodium hydroxide to be 0.1, then the concentration of the hydroxide ion will also be 0.1 moles per decimeter cube. So how can we calculate the pH? Because we don't have here a hydrogen ion concentration. We have an OH minus. So from where can we get the concentration of the hydrogen ion to calculate the pH? Now, from a moment we said that we have something called the ionic product of water, which is Kw, which is equal to 1 times 10 to the power minus 14. And we said that the Kw equal the hydrogen ion concentration times the OH ion concentration, isn't it? So if I want to calculate the hydrogen ion concentration to get the pH, it's going to be 1 times 10 to the power minus 14 divided by the concentration of the OH ions. So if we got the concentration of the OH ions, for example, to be 0.1, so just divide 1 times 10 to the power minus 14 over the concentration of the OH ions, which is 0.1, we get the hydrogen ion concentration, and from which we calculate the pH, which is equal to minus log the hydrogen ion concentration. Understand, Maya? Should I repeat this?
No, miss, I understand it.
Okay. Now let's take examples. It says calculate the pH of a solution of sodium hydroxide of concentration 0.05 moles per decimeter cube. And he gave us the Kw equal 1 times 10 to the power minus 14. So here we said that sodium hydroxide completely ionizes to give sodium ions plus OH ions. Of course, we don't mind the sodium ions. So if we start with 0.05 moles per decimeter cube of sodium hydroxide, this means that it completely ionizes to 0.05, of course, of both. But we are going to consider only the OH ions. Now, we said that Kw equal the hydrogen ion concentration times the OH ion concentration. And we said that Kw is 1 times 10 to the power minus 14 equal the hydrogen ion concentration that we don't know times 0.05, which is the concentration of the hydroxide ion. So the hydrogen ion concentration equals 10 to the power minus 14 divided by 0.05, and we get the number. The number here was 2 times 10 to the power minus 13 moles per decimeter cube. So to calculate the pH will be equal to minus log this value, which is 2 times 10 to the power minus 13. And if we do this in our calculator, we'll get a value of 12.7. And yes, before we said that pH of the alkaline solutions ranges from 0 to 14. So 12.7 lies in this area, which makes sure that our solution is a basic solution or an alkaline solution. Okay. There's another method. We can do it in our calculations. This method is completely right, but we have another method for calculating the pH. So you can either calculate it in this way or in the other way. What is the other way? The other way is that we said that the Kw equal hydrogen ion concentration times the OH ion concentration. So we can take minus log both sides. So we say that minus log Kw equal minus log the hydrogen ion concentration minus log the OH ion concentration, because from the log properties, if we have two values that are multiplied together, we can take log of the first plus log of the second. If we have two values multiplied together, we can, and we want to take the logs, then it will be log the first plus log the second. But we are taking minus log, that's why we said minus log hydrogen ion concentration. So we say plus minus log OH ion concentration. So it's minus log both sides. Okay. Now we said that minus log means P. So here we say pKw equal pH plus POH, because P means minus log. So we say that the pKw equal pH plus POH. So here Kw has this value, 1 times 10 to the power minus 14. So if on our calculators we get minus log 1 times 10 to the power minus 14, we get a 14. So we say 14 equal the pH plus the POH. This is another rule to calculate the pH. Now here, for example, in our problem, we had the concentration of the OH ions to be equal to 0.05. So if we take minus log the OH ions, which is minus log 0.05, we get a value of 1.3. If we take the minus log the hydrogen ion concentration to get the POH, it means minus log the hydrogen ion concentration. We get it to be minus log 0.05. We got this value 1.3. So we say that the pH equal 14 minus the POH, which is minus log the concentration of the base, equal 14 minus 1.3, and we get the same value, which is 12.7. Understand me? Or shall I repeat this method again?
Miss, can you repeat it, please?
Yes. We said that Kw equal the concentration of hydrogen ion times the concentration of the OH ions, isn't it? This value times this value. So we are going to take minus log both sides. So we say minus log Kw equal minus log the hydrogen ion concentration plus minus log the OH ions. This is from the log properties, that whenever we have two values that are multiplied together to form the logs, we take the log of the first plus the log of the second. So here we have minus log Kw equal minus log the hydrogen ion concentration plus minus log the OH ion concentration. This means plus minus means minus. So minus log the Kw equal minus log hydrogen ion concentration minus log the OH ion concentration. Okay. Of course, you are not going to do all that. I'm just showing to you how we got this rule. So minus log means P. When we say pH, it's minus log the hydrogen ion concentration. So P means minus log. So we take minus log, we put instead of it pKw equal minus log hydrogen ion concentration, we are going to put pH plus minus log OH ions, we are going to write POH. Now the Kw has this value 1 times 10 to the power minus 14. If you take minus log 1 times 10 to the power minus 14, you will get this value, which is 14. 14 equals the pH plus the POH. So if we know the concentration of the OH ions, for example, here 0.05, so P means olna minus log. So minus log the hydrogen ion concentration equal minus log 0.05. So we get this value, which is 1.3. So if we substitute 1.3 here, and here it's 14, so the pH will be 14, and we get this value the other side, pH equal 14 minus the POH equal 14 minus 1.3 equal 12.7. Or else, if you don't understand this method, just write as we did before, that the Kw equal hydrogen ion concentration times OH ion concentration. So the hydrogen ion concentration equal the 1 times 10 to the power minus 14 divided by the concentration of the OH. You get the concentration of the hydrogen ion, from which you get the pH. Either you use this method or this method. Both are correct. Okay, Mai? Understand?
Yeah.
Okay. Now, what if we have a weak acid? If we have a weak acid, like for example, ethanoic acid, we said that weak acids partially ionizes in water. They do not completely ionize in water. They partially ionize in water to give the hydronium ion plus the, for example, if we start with ethanoic acid plus water, we get hydronium ion plus ethanoate ion. Or else in a more simplified equation, we write that the ethanoic acid at equilibrium gives hydrogen ion plus ethanoate ion. The arrows that represent the equilibrium means that ethanoic acid partially ionizes. It means that a very small amount of it ionizes to give hydrogen ions plus ethanoate ions. So here, if we have a weak acid like ethanoic acid, and this ethanoic acid partially ionizes in water to give the hydrogen ion and the ethanoate ion. So we said that whenever we have equilibrium, then we have something called the equilibrium constant. But here we are going to call it the acidity constant, because we are dealing with an acid, because we are dealing with ethanoic acid. So Ka, which is the equilibrium constant with respect to an acid, equal, we said it is equal to the concentration of the products times the concentration of the acid. Okay. Now, we say that ethanoic acid is a weak acid. It partially ionizes. It means that if we start here with 100% of ethanoic acid, then after ionization, we will get only 99% still present in the form of ethanoic acid and only 1% dissociated into hydrogen ions and ethanoate ions. Sometimes they say 1%, and sometimes they range it between 1 and 10% dissociated into hydrogen ions and ethanoate ions. Now, in order to simplify our equation, we are going to consider the concentration of the ethanoate of the ethanoic acid to be constant, because only a very small amount of it dissociated into hydrogen ions and ethanoate ions. So we are going to multiply. We are going to say no. Okay, don't say here this. Yes, it's considered to be. Yes, it's considered to be constant. The concentration of hydrogen of ethanoate ion is considered to be constant. Yes, this is an approach. But here, as we said, that hydrogen ions and ethanoate ions are equal in concentration. So we can remove the ethanoate ion and write H positive squared divided by the concentration of ethanoic acid equals Ka. And this means we want to calculate the pH of the weak acid. So we are going to put the hydrogen ion in one side equal, we are going to multiply Ka by the concentration of ethanoic acid. Okay, so the hydrogen ion concentration equal the square root of Ka times the concentration of the ethanoic acid. We are going to consider as if the ethanoic acid is constant, concentration is constant, as if it didn't dissociate, because its dissociation is so small. So here we are going to substitute by the value of ethanoic acid that we got at the beginning of the problem is going to give us a concentration of the weak acid at the beginning. And in order to calculate the hydrogen ion concentration, we are going just to write that the concentration of hydrogen ions equal the square root of the acid dissociation constant, which is the equilibrium constant, Ka. We call Ka the acid dissociation constant. The acid dissociation constant. So Ka, which is the acid dissociation constant, times the concentration of the ethanoic acid, as if it didn't dissociate. We take the square root of this, we get the hydrogen ion concentration, from which we say that the pH equal minus log the hydrogen ion concentration. Okay, so for a weak acid, in order to calculate the pH, we are not going to take minus log the concentration of the acid at once, as we did in case of strong acids. In case of strong acids, we said, for example, if he gives us the concentration of hydrochloric acid, for example, then we are going to take it as if it is the concentration of the OH of the hydrogen ion as well, because HCl completely ionized to hydrogen ions. So the concentration of HCl is the same as the concentration of the hydrogen ions, and at once we say pH equal minus log 0.1 at once. But in weak acids, we have to introduce the acid dissociation constant, which is the Ka, because the acid partially ionizes. We cannot take the hydrogen ion concentration the same as the concentration of ethanoic acid, which is the weak acid, because only a very small part of it dissociated, not all of it like in case of HCl. That's why we have to consider the acid dissociation constant, Ka equal hydrogen ion concentration times ethanoate ion concentration divided by the ethanoic acid concentration. And here, since both hydrogen ions and ethanoate ions are equal in value, then we have to remove this ethanoate ion concentration and put instead of it H positive squared. H times H means H positive squared. Okay, and in this way, the hydrogen ion concentration equal Ka times the concentration of the ethanoic acid, or else the hydrogen ion concentration equal the square root of Ka times the concentration of ethanoic acid, and the pH will be equal to minus log hydrogen ion concentration. So either you have to know this rule, or else you can do it from the beginning as if you want. Either you do it when you are solving the problem, either you do it from the beginning, or else you study this rule that the hydrogen ion concentration for a weak acid equal the square root of Ka times the concentration of the weak acid. Of course, this rule is derived from these steps. So either you do these steps or else you know this rule. Okay, understand, or shall I repeat it?
No, I understand. Thank you.
Okay, now you're welcome. Now, here we have done two approximations. The first approximation is that we considered the concentration of the ethanoic acid after being dissociated as if it remained as it is, because here this is the concentration of the remaining acid. So here we considered that it's the same as the starting concentration of the acid. This is a first approximation we did. And the second approximation is that we didn't introduce water in the equation. Here, ethanoic acid to dissociate, it must be present in water. But for making simplification, we didn't consider the water entering in these calculations, although it is present. So this is a second approximation. Sometimes they say, what approximations did we did on calculating the hydrogen ion concentration of a weak acid? Then the first approximation we did is that the concentration of ethanoic acid was considered to be constant, as if nothing was dissociated out of this ethanoic acid. This is the first approximation. And the second approximation is that we didn't consider water in our calculations, although it is present in the solution. Okay.
Okay.
Now, let's try to solve an example for these calculations for a weak acid. Of course, here they are just giving you, before we solve the problems, they say that whenever we have, we said that we in this equilibrium, we have an acid dissociation constant, Ka. The more or the higher the value of the Ka, this means it's a strong acid, because Ka measures the concentration of the hydrogen ions times the concentration of the ethanoate ion. For example, if we are talking about ethanoic acid, divided by the concentration of ethanoic acid. When Ka is high, what does this mean? It means that the concentrations of hydrogen ion and ethanoate ion are also high. Of course, not in this equation, but for other acids. When we have a high value for Ka, this means that this equilibrium is shifted towards the right-hand side, as if it is like in case of strong acids, we say that the reaction shift towards the right-hand side, towards the formation of the hydrogen ions and, for example, the chloride ions. So if we have a high value for Ka, this means that this equilibrium is shifting towards the right-hand side, towards more ions. And this means that the acid ionizes more and more to the hydrogen ions and whatever, the other negative ion. But when we get a low value of Ka, this means that this reaction is not favorable, but the opposite reaction is the one that is favorable. And this means that, the acid partially dissociates into water. So the more we have a higher Ka value means that we have a strong acid, because scientists say that we don't have any acid that 100% dissociates, but strong acids nearly 100% dissociates. But there is also an equilibrium here, but the equilibrium lies further to the right-hand side. But if we have a weak acid, then this equilibrium lies further to the left-hand side. So the more or the higher the Ka value, the stronger is the acid. For example, if we take nitric acid or sulfuric acid, we will find that this equilibrium, as we said, that they are going to consider that all acids equilibrate. But if it's a strong acid, this means that the equilibrium shift towards the right-hand side. So here, if we have nitric acid or sulfuric acid, we will find that the Ka values are very high. The Ka value of nitric acid is about 40. It's a very high value. And for sulfuric acid, no, this is not sulfuric, this is sulfurous acid. The sulfurous acid, we find it 1.5 times 10 to the power minus 2. Hydrofluoric acid is 5.6 times 10 to the power minus 4. Ethanoic acid, it's 1.7 times 10 to the power minus 5. You see, water is 10 to the power minus 14, the Ka value. So this means that as we go down, the acidity decreases. This means that nitric acid is the most stronger acid of all. The strongest acid of all is nitric acid. And of course, as these values decreases, this means that we are coming to weaker and weaker acids until we get to water, which is a very weak acid, 1 times 10 to the power minus 14. So the higher the Ka value, the stronger is the acid. But the pKa value is the opposite, because P means minus log. You take the minus log of this value. So you will find that the more the value is smaller, means the pKa value is smaller, means that it is the strongest acid. You understand? Ka is opposite to pKa. For Ka, the higher the value, the stronger is the acid. For pKa, the lower the value, the strongest is the acid. Okay, understand? Shall I repeat this? Hello?
Yes, Miss, can you hear me?
Yes, I can hear you now.
Okay.
Okay, so Ka is opposite to pKa. The higher the value of Ka, the strongest is the acid. The smaller the value of pKa, the stronger is the acid. Okay, they are opposite to each other. Understand, Maya?
Yeah, okay.
Okay. Now, calculating the Ka for a weak acid, as I told you, of course, that a weak acid, if we take this in general, the weak acid Ha, it's a general, of course, symbol to a weak acid. Ha partially ionizes into hydrogen ions and A minus. And since we have hydrogen ions and A minus, they are equal, then we can remove the A minus and put H positive instead of it. Ka equal hydrogen ion concentration times. Hello?
Yeah, Miss, I can hear you now.
Okay, I'm going to change my net.
Okay.
Hello? Hello?
Yes, Miss, now I
Can you hear me now? Okay. Now, as we said that for a weak acid, Ha giving hydrogen ion concentration plus A minus, then we have the acid dissociation constant Ka equal the concentration of H positive times A minus over the acid Ha. And so we are going to remove the concentration of A minus and replace it by an H positive, because both are equal. So we say that Ka equal hydrogen ion concentration square over the Ha, and from which we can calculate the hydrogen ion concentration. So here we are going to solve this worked example to find the value of the pH of such a solution of a weak acid. So for example, here it says, calculate the value of Ka for methanoic acid, which of course is a weak acid, since even if you don't know, when he says calculate the Ka, it means that it's a weak acid. A solution of 0.01 mole per decimeter minus 3 methanoic acid has a pH of 2.9. Now, he gave us the pH value, and he wants the Ka. Now, methanoic acid, if we consider it Ha, it partially ionizes into hydrogen ion plus methanoate ion. And this means that we have the acid dissociation constant Ka equal the hydrogen ion concentration. And we said that we are going to remove the A minus and put instead of it another hydrogen ion, as both are equal. So the Ka equal the H positive squared divided by the concentration of the acid itself. Now he gave us the concentration of the methanoic acid to be 0.01. This is the HA, it is 0.01. And he wants us to calculate the Ka. But in order to calculate the Ka, we have to know the hydrogen ion concentration. He didn't give it to us, the hydrogen ion concentration, but he gave us the pH. It's equal to 2.9, from which we can get the hydrogen ion concentration, because we said that the hydrogen ion concentration, you are going to write 10 to the power minus 2.9 on your calculator and get it. So if we do that, if we put, or in my calculator, I'm going to write shift log and then put between brackets minus 2.9. This is equal to 1.258 or 1.26 times 10 to the power minus 3. This is the hydrogen ion concentration. So we are going to substitute this value in the law to get the Ka. So the Ka equal 1.26 times 10 to the power minus 3 squared divided by the concentration of the acid that he gave us at the beginning, 0.01. And we get the Ka value, this one, which is 1.59 times 10 to the power minus 4. If we do this calculation, we will get 1.59 times 10 to the power minus 4. Okay. Understand?
Oh,
Shall I
yeah.
repeat it?
No, I understood.
Okay, thank you. Now, if I want to calculate the pH of a weak acid, as I told you from a moment, that here it says calculate the pH of 0.1 mole per decimeter cube ethanoic acid, and he gave us the Ka. Whenever he gives us the Ka, this means this is a weak acid, and this means that dissociation takes place partially, not completely. So it says calculate the pH of a 0.1 mole per decimeter cube. He gave us the concentration of the weak acid, and also he gave us the Ka. And as we said that Ka equal hydrogen ion concentration squared divided by the concentration of the acid itself, of ethanoic itself. Okay, now this means that the hydrogen ion squared equals the Ka value that he gave us, 1.74 times 10 to the power minus 5, times the concentration of the acid, which is 0.1. So we do these calculations, and then the hydrogen ion concentration is equal to the square root of this value that we get. So here we got 1.74 times 10 to the power minus 6. So we get the square root of this value, which is equal to 1.32 times 10 to the power minus 3, as he gave us here. And so the pH will be equal to minus log this value, which is 1.32 times 10 to the power minus 3. And we get the pH value to be 2.88. Understand this method, or shall I repeat it?
No, I understand.
Okay, thank you. Now, when we do titrations, as you remember that titrations is an experimental method that is carried out between an acid and a base or an alkaline solution. For example, if we have an acid that we do not know its concentration, so we do what we call a titration together with an alkaline solution in order to determine the concentration of the acid. Or the opposite, if I have an alkaline solution that is with an unknown concentration and I want to determine its concentration, then I have to make a titration between an acid with a known concentration in order to get the concentration of the alkaline solution.